Okay, thank you everyone for coming to the second talk of the session. So we've got Sean Gryb from the University of Bristol, who's worked extensively on shape dynamics and the problem of time, and he's going to talk about time, scale, and symmetry in gravity.
No, it is. Okay. All right. So I want to thank the organizers for inviting me to the conference. Actually, Julian explained it. Fabio couldn't make it. He's the one that wrote the book on shape dynamics, which you should totally buy and not download off the internet. But unfortunately, well, the kind of technical version of the shape talk that continues on part of what Julian was introducing this morning. So, okay, as you could perhaps tell from Julian's talk this morning, shape dynamics is a theory that defies GR orthodoxy. So there's a lot of elements of shape dynamics with relativity. One of the interesting things as being part of the program, seeing the program develop, was realizing that things that you might not expect are actually true even in the general relativity. Just you have to kind of change the way you think about them. Oh, you're already asking a question. Oh boy.
How far is it just a question of interpretation, and in what sense is it really physically different in the sense that predictions differ?
Good. I'll get to that. Yeah. That's going to be my talk, I guess. Well, okay, to preview that, so the way I'm going to do it is divide into two phases. Okay, I think that's a nice pedagogical way of thinking. One phase is to talk about, to just kind of split local versus global observables. Okay, so from the local point of view, I think it's just a reevaluation of the local observables. Sense of, let's just take general relativity the way it is, analyze it, and look at the symmetries, and then see that there are kind of hidden symmetries within general relativity. And then you can kind of reinterpret that in a way. And Julian said this morning. I mean, Julian really feels that the scale invariant interpretation is more fundamental. And so that is an option or not, right? So part of the way we defy GR orthodoxy, evaluate what you think of as a local. The second thing is to question what it means for an observable to be global, and like what I'm going to get to is that the global scale is going to be treated slightly differently in shape dynamics from in general relativity, and this could have implications to cosmology, to other things, to the arrow of time. We're still working out the details on that. This is going to be the result of a technical thing that we illustrated. This is going to be the beginning of a research program which we're only in the kind of what I call like phase 2 of shape dynamics. And the more ambitious goal is to go beyond general relativity. We're not quite there yet. We don't have research, but once we understand what we're doing here, then is to use that as a way to talk, perhaps make progress in quantum gravity. But again, something that Julian highlighted, what is described that's put into general relativity. It's the kind of thing that we think shape dynamics will hopefully be able to shed light on. And so these are touching on a lot of questions that we already had earlier. Hopefully I'll be able to get into more detail in this talk. So more specifically, phase 1 started with an unexpected observation. It was unexpected to me, and I think that a lot of people are surprised when they hear this, which is just that local observables in general relativity are scale invariant in a very specific sense that I'll get to in a bit. Secondly, it's going to be a critique. GR are not giving us a faithful representation of observations. And this is going to have to do with the global scale. So I'll get to that in a second. And finally, I already said this. What we really want to do, I think, right, this is an aspiration of most of us, is we want to have a kind of fundamental shape theory that will constructively describe measurement instead of putting it in as a prior. And that should really take us beyond general relativity in principle. Okay. let me start with the 3 words that are in my talk, and these are just going to be a couple seed what's going to happen later, because like I said, I'm going to defy orthodoxy. So I'm going to say things that are going to be shocking to you. And right now, the kind of so that actually happens. Okay, so the first thing I say, and this is something I do all the time, and actually the shapers are probably a bit their eyes when I do, but it's still to do it, and it will come back to it. A statement, what is scale? So all measurements are quasi-local comparisons. This is my claim. So if I want to measure the pen, what do? I want to compare it to something else that also has a length. So I do one of these, and I find that it's approximately 3 times, 4 times. This pen is approximately 4 times the length of this probe. Okay? And sophisticated versions of that measurement. And the important thing is that it's a comparison, right? And happens in more or less local regions. If I rescale space in a different way, provided that rescaling is smaller than the size of the measurement, I can carry my rod and my thing that I'm trying to measure over here, do the same experiment, and even though space may be 4 times bigger over here than it was over here, that's still not going to change the result of the measurement. Okay, and so this is going to motivate principles. Well, basically the same principle, and I would say that one of them is just the first observation. Pretty solid epistemic argument that global must be surplus structure. It must be some artifact of our representation of physics that doesn't exist in the real world, because objects are visible to it. That argument.
Is that a claim about every physical theory?
Yes. Yeah. Over that, there's this now quasi-local thing where I locally solid of a. We don't really understand the word quasi, right? Yeah, that's true.
So it's not a solid epistemic argument.
No, I didn't say global structure, I said global scale. Yeah. Oh, there are global properties of space-time that might not be, yeah. Okay, so, so this is a kind of, so what I case differently would be this kind of Weil transformation, which is you take the metric, this is spatial metric, okay, because I was talking about lengths, I wasn't talking about proper time ratios, I was talking about length ratios, and you rescale them. That's a Weil transformation or a conformal transformation. So you might say, however, okay.
Could I?
Yeah?
I mean, maybe I just want to put some words into your mouth and see if you spit them out. Why can't you just say that that what we want to do is disentangle predictions from definitions? So whenever we want to specify what we do in an experiment, we need to have some reference structure, some dials that we tune, and some pointer that gives us an outcome of whatever some quantification of the outcome. But that needs to be done in terms of physical stuff, the things that already exist.
Yeah.
And so when we want to describe physics as a whole, so the universe as a whole, then we have to take into account that we cannot use the semantics of all this reference structure, but that we have to explicitly say, I'm comparing. I mean, you made this point with the marker and the cap, you said 3 times the length.
Good.
But that is quite general, and I don't think any.
It's pretty general, and I think that argument is good. I haven't yet really found a rock solid argument for that, but it doesn't really matter, because what I was about to say is that there's another reason, which is fairly convincing, which is actually what got me really interested in this originally, which is that GR has this, I'm calling it a hidden spatial Weil symmetry. So that is one of these places where people are going to be like, that's totally nuts. I'll tell you that in a second.
Sorry, just one thing. One thing with the cap that people might say is, in fact, look, you don't measure these things at an instant. In fact, what you measure are light rays, and so it's what you should be thinking about is spacetime by space.
Yeah. Okay. Let's just leave this as one of the part of the to-do list for us. But this fact here, I heard the talk, that you were more impressed with this argument, the technical result coming out of shape dynamics, than with this one. Anyway.
I agree with you.
Yeah.
I will say something.
Okay. Good. And he's going to talk about it in his talk too. So now I want to talk about time, which is also going to. Oh boy.
I'm really sorry to say that. The jitter is spatial. Will you be saying why it's not spatial temporal, or do you just?
Yeah. I'll explain.
Can I make a suggestion? We let Sean finish his intro.
I knew it was starting bad before I even. Okay. Good. If we just have discussions, that's fine. This is something I really do want to say. Next was something that I think George was saying in a different way in his talk. I want to say I don't really want to say what is time, because I don't want to talk about simply duration. We all agree on is that duration is a measure of change. Now, what I make is that change. Okay, so if I want it. So how do I, because the hands have moved, right? Moved over. And that's an objective change. If I take that clock and close to the speed of light, if I bring it close to a black hole, if I do all the kinds of things that GR tells us are going to create some kind of time dilatational effect, that's an objective. I can bring it back over. And I compare it to a similarly made clock that's ticking. True, but that's an objective process that's happening in the world, right? It's not effect. GR is telling us, yes, GR is formulated in a diffeomorphism invariant way, but it's doing that so that it can capture physics, which is that process that we want to describe. So if we can describe that process in some simultaneity surface, then we're done. That's all we really need to do. So I think what I wanted to say, because, and this I think is effectively what George was saying in a slightly different way, that time labels are arbitrary in general relativity, but the processes themselves are not, and those are things that are really happening actively. Okay. And so the reason I'm trying to plant this is that scale invariance, the kind of Weil invariance I was talking about, happens in a particular choice of simultaneity. So the idea will be you choose a simultaneity class, and that process. Okay.
For GR, I mean,
Yeah. Say so it was what? It was scale, time, and symmetry. So I want to claim is surplus structure, like the Redmond idea of talking about symmetry as surplus structure. It's extra stuff that representations of the world but may not be the real world. That's why I call it representational underdetermination. Now, I want to make a clarification because I think there's two different notions underdetermination, two different ways that things can be underdetermined that I want to flag because they will be importantly different later. Mathematical underdetermination, and what I mean by that is that you can have mathematical theory literally it could be something like just a matter of introducing arbitrary functions into your mathematical representations that will then your theory. The kind of representational redundancy that you have in typical gauge theories. Okay, and those functions would be Lagrange multipliers or whatever, gauge parameters. There's another kind of thing that could happen, which is actually interesting when it does, is that your representation is completely underdetermined. So you can have well-defined equations of motion may be underdetermined physics. And an example of this would be, what is the momentum of a Newtonian universe, right? So, I mean, you can write Newtonian theory, but I don't do observation, so I can. The is going to be that local scale is physically underdetermined, and this is going to lead to real differences with GR. Okay, so that was my long-winded introduction. How much time? Okay. I think those are true. Start with something we called symmetry to construct shape dynamics, but actually because then I'm going to mention what I call Barber's shape hypothesis. So it's effective go through and tell you how everything works. Okay. Convenient truth. Most gauge theories, this is a fact that for some reason most people either forget or they put in the back of their minds when they first learn about gauge theory and they don't remember, is that the total redundancies in a gauge theory are not always, but in many standard gauge theories, bigger, in fact double, the total amount of Lagrangian level. So let me give you a degree of freedom counting, right? If I have a Maxwell field, a free Maxwell field, in 3 plus 1, I have 4 vector fields, and but only polarization directions for the electromagnetic field. And this is a calculation. The rank of the Hessian of the Lagrangian for the Maxwell field is just 2. There are 4 degrees of freedom. There have to be 2 symmetries per point. One of them is obvious. But what about the other one, right? The one that nobody talks about. Lagrangian level, I've never really found a really, maybe that's just because I don't know, but I've never found a convenient way of representing these other symmetries. As far as I know, the best way to actually think about this is in the Hamiltonian framework. So let me just very quickly review the Hamiltonian framework. Here, symmetries are represented by symplectic flow of constraints. So, I don't have the pictures here. Okay. Example, again, free Maxwell field. Everybody knows. Well, the Hamiltonianism, you've got the vector potential and the electric field, and there also have the zero component of the field potential and then its momentum. Now, the constraint is a first class secondary constraint in the formalism, but right, you know this from second year The canonical U1 symmetry, okay? Under a zero equation, so it doesn't have a momentum. The one that we always know. These to see what these symmetries levels more. And what I wanted to say, is that what are these symmetries? It's because you're looking for symmetries of the variational principle. You can also just generating things that are zero on shell. So if there are changes, and let's not forget about these, right? So now let's play a game with this extra freedom, okay? And one of the games you could play, and this is what something like the Gauss constraint. Now the idea is, if you're not familiar, the directional derivatives of these constraints, on the constraint itself, we call a gauge orbit. So these gauge orbits are just all, in electromagnetism, different values of the kind of the part that's gauge. And so each element of this line is the standard picture in gauge theory, gauge fix. So you want to cut this surface with another surface that cuts all of these gauge orbits exactly once. And that will eliminate see from the theory and give you a kind of well-determined at the intersection here between these two surfaces. So this intersection, when you draw it on a piece of paper, looks like a line, but it's some higher dimensional thing. Okay. Now that's the standard story, but all you need to do is say what happens if you swap the role of the gauge fixing surface and the gauge generator, and you just say, well, I can think of this as a theory that has a symmetry generated by what was the gauge. The gauge generator of the first theory is now the gauge fixing of the second theory. Obviously, it's still the intersection. The intersection is the same. So I can equally think of a new kind of gauge theory, or this other representation of the same gauge theory, as a physically equivalent version.
In fact, the physics should live in a projection.
Yeah, that's true. That's true. Yeah, okay, fair enough. That is true. So physics lives on some dead space that I didn't draw, but as this intersection. Okay, and so that works. I can go into the details of this, but this is that's all it is. You have theory 1, it has symmetry 1, and so the way I like to think of it is that this is just representations of the same gauge theory, where in one case the first symmetry is manifest and the second one's hidden. It's manifest because you can see it at the level of the Lagrangian. And in theory 2, the second theory is manifest, the other one's. The symmetry of changing which symmetry is the one that you see. Okay? And we actually did this formally because it gets complicated because we have differential operators, is to construct a linking theory. Is you can, by extending the phase space, you can introduce a symmetry, and then you have a theory that has both symmetries. Then the idea is what you can prove is that if I gauge fix symmetry 1, I get theory 2. Or I could start with this bigger theory, gauge fix symmetry 2, and get theory 1. And then I can go to the section fixing. They're all just different gauge fixings of one common linking theory. Different representations of the same physics. So it's just a different way of thinking of it. Okay, good. So where are we now? There we go. So now I want to get to the second part of the talk, which is this have to do with shapes. So this is going to be my reading through. Oh, you can interrupt me. That's fine. I'm doing my best. So let's just world is in principle knowable, right? That there's a God's eye. There is a kind of the theoretician's view of the world that allows you to think of a law and conceive of a law that you can define on the things that make up the world. And the things that make up the world, the things that make up the world are the shapes. But before I want to say another thing, which is that you might think that it should be a closed system, okay? So the actual world is a closed system. There's no external things that are coming in and affecting it. Otherwise, that would violate the first principle in some sense. So once you have that, then the next thing is in the world. And I think for Julian, it's just clear that what's in the world are shapes, okay? And at this point, you don't have to even really define shapes. You can just say, the shapes are what are part of the world. And then the last thing is that, well, we are just shapes that are making measurements of other shapes. I put conjecturally here because I think this kind of open research question, exactly how to think about this. Obviously, I talked about this at the beginning. We want to model the observation process. And part of that is understanding people happen. In particular, how stable structures emerge from the dynamics of the theory. And so Julian conjectured in a book a long time ago, although it's thought that stable structures are something like time capsules. So these basic principles motivate several hypotheses. So is, how are we going to represent these shapes? Okay. This morning, Julian was talking about using angles of triangles, right? But another way, if now we're talking about gravity, what we might want to do is represent as Weil invariant 3 geometries. These are going to be represented by geometries up to some conformal class. We're going to put these on a spatially closed manifold, because if it wasn't spatially closed, then the universe would be an open system. And then finally, he will talk about classical histories as dense ordered sets of these shapes, a curve of shapes. But I feel like, and correct me if I'm wrong, but this is the one damn shape after another, right? So the ordered history, but that these are, and this is the reason why we have to put this point here, is that I think this is true that Julian believes that these structured ordered sets should come as emergent structures out of something like quantum mechanics, yet to be determined. So I don't think Julian thinks that these classical history curves are out of just the space of shapes. Okay, so I write this because I feel like this is the extreme view, right? This is the ultimate goal, or at least this is Julian's intuition that he's been developing over the years. And I think different people in the shape dynamics community ascribe to various versions of this at different, right? So Enrique is going to talk something like how he thinks records can emerge. Is how ordered dense sets of shapes can be representing classical general relativity. And so I put that up because I feel like this is the extreme view. Okay, so now how can we take these hypotheses and try to turn them into a theory? Obviously, what I just described to you doesn't really look a lot like general relativity, okay? But in '73, York had this paper where she starts off, and increasing amount of evidence shows that the true degrees of freedom of the gravitational field can be identified directly with the conformally invariant geometry of three-dimensional space-like hypersurfaces in time. So that actually sounds a lot like Julian's in space-time part. Where did he come up with that? What drove him to come to this conclusion? The answer is that he found simultaneity, found a gauge the constraints of general relativity, where and so the idea is to try to use slicing to do symmetry trading, but that's one way to think of it. To use symmetry trading and then show that you can have a gauge theory of conformal invariant three geometries. So that's what we did. Well, that's what we did. Although we were built, I should say that we built on a lot of work that Julian talked about in his talk that came before us in 2005. Okay. So this was our idea that the York slicing used slicing to identify three-dimensional conformal symmetry as a hidden symmetry of general relativity in the way that I talked about.
For a vacuum.
For vacuum first, but that was.
It extends to matter.
Yeah,
Absolutely.
I'll talk about that.
Model field.
Talk about matter in a second. For now, we're just talking about gravity free. Okay, so good. George mentioned this in his talk. You can decompose space-time metric into three metrics evolving in time. So this is the Hamiltonian formulation. The variables are three geometries and their momenta. There are multipliers which wind up being related to the now, the key thing is that you can break up the symmetries into two different classes. One of them are the three-dimensional coordinate transformations on a slice. So the idea is here is a space-time that I've sliced into space-like hypersurfaces, and I can do coordinate transformations on these three slices. So those are the three, and those are actually fairly simple. But there's also the time of these time diffeomorphisms, just what we call hypersurface deformations. So you can take the same space-time, and you can slice it up differently. And that should be a symmetry of general relativity. The claim is that in the same way that the Gauss constraint generates the U1 symmetry of electromagnetism, the Hamiltonian of the ADM Hamiltonian generates hypersurface deformations of a space-time. Now, what did York show? He showed that the ADM Hamiltonian can be gauge fixed by the generator of Weyl transformations. So I think I have a picture here, which is, again, I've suppressed the diffeomorphism constraints because, like I said, they play a background role. But that's non-trivial, by the way. So you have this ADM constrained surface on the GR phase space, and there's this conformal generator, which York used to gauge fix general relativity. then you could just say, yeah, but if we've gauge fixed it, we can also just move up here. We can trade the roles of the hypersurface deformation generators and the conformal generators to think of this as a gauge theory of Weyl transformations. And so in particular, so this would be the Einstein equations, and then other curves on this would be some sort of refoliated solution of the Einstein equations. Then if I move along these conformal orbits, I can generate other solutions that would be different shape dynamic solutions. They would stack up into a space-time. They wouldn't be solutions to the Einstein, but the gauge invariant degrees of freedom would be the same. So the idea is that because the physical processes that I was talking about, the moving the clock into the room, those physical processes are described just on this intersection. So through these different conformal classes won't change the predictions for those physical processes. That's the idea. Okay. And then we constructed this linking theory. I guess the details are probably not that important. Prove this is linking theory. We showed that if you this is a theory that has all of the transformations, and I write this because Stefan's going to talk about some version of the linking theory in his talk. Because after we came up with this, we sort of forgot about the linking theory. Partly, if the physics lives here, then we should just be looking at this. And I think Tim is going to really emphasize that in his talk. I think Tim has moved away from this idea of the linking theory and more toward here. However, by trying to understand this, that's going to be what Stefan will be talking about. But here you can gauge fix the Weyl transformations and you get back to ADMGR. If you gauge fix the hypersurface deformations, you get some Weyl invariant theory, which we call shape dynamics. And then if you do the opposite gauge fixing, you can get to this kind of reduced theory. Okay. So, but there's a caveat. And this is going to be the last thing I really want to say that much about. But this is the thing so I've been talking about phase 1 of shape dynamics. This happened like 8 years ago and even well before that. But there was this really thing that puzzled us at the beginning that, now I said gauge fixing, right? But I was actually not that careful because if you really cut the Hamiltonian is the thing that generates time evolution as well as hypersurface deformations. So if you gauge fix the Hamiltonian, then there is no time evolution. You're just stuck at an instant. And so what you need to do, well, the way we thought of it originally was that, we'll gauge fix all of the modes of the Hamiltonian constraint except for one. Except for the one that's generating the time evolution. So all the ones that are kind of generating hypersurfaces will fix with a conformal constraint. But there'll be one leftover Hamiltonian, which is literally the York Hamiltonian. It's the part of the ADM Hamiltonian that evolves you in this special gauge. Will be free. And that was a bit of a puzzle for us at the time, because what it meant is that we could get rid of the local scale, but we were still left with one global scale, because if we couldn't trade that, we couldn't get rid of the global scale, right? Because the scale and the time. But, which I think is solid, that the global scale is the thing that's unobservable, the thing that drops out of our real observations. So the idea would be, if general relativity really modeled observations properly, this is going to be the theme of that notion of scale theory.
Sorry, it wasn't very clear to me the distinction between the global scale and the local scale.
The global scale is just It's the volume. Okay, the volume, the 3 volume of the universe.
I
How about that?
Okay.
What do you want me to say?
Why you're separating just in the philosophical treatment of it? You said there was these physical redundancies and mathematical.
Oh, right, yeah.
And
Okay.
Yeah.
Because they're all the measurements are comparisons. If I rescale everything in the universe same everywhere, that's going to that's not going to be something that I'm going to pick up in any observation, independent of whether I move this around over here. So what I was saying at the beginning was that the epistemic argument against scale is local scale. Okay, and that motivates this thing called dynamical symmetry. It's not something that we actually invented. Is something that we rediscovered. Neil Amorahou, working with Julian, noticed this. Dave Sloan noticed it completely independently of us. It's also something that if you're a cosmologist, an undergraduate, you learn this in one of your first courses, that the solutions are dynamically that they have a symmetry where you just pull a constant. I can, that's not going to change the variational principle. It's in solutions to solutions the same. So in the solar system, you could imagine doing scaling the energy and then rescaling the time in such a way that the orbital time stays the same. That's right? And so this is what people knew, except that if you have stuff and clocks that are external, then it's a bigger system because it's now you've rescaled the energy so it looks larger compared to the energy of stuff outside. Even though people notice that Newtonian n-body has this symmetry, it's mapping solutions to physically distinguishable ones. By the same argument, if you say, forget about everything outside the solar system, what if we're now talking about the universe? What if we're trying to do cosmology? Then there are no ways a closed system. Then these solutions are physically indistinguishable. We don't have the difference between these solutions. I think is that nobody's ever thought to quotient by this symmetry, right? So even though there's a very strong epistemic argument to motivate this symmetry, it's still sitting there, and it's playing a very similar role to the momentum in Newtonian theory, right? That exists in our representations, but is underdetermined by the physics. And so this is where I say I think for cosmology, this insight could be really important, and it could change the interpretation, and Dave's going to say a lot more. So that's phase 2, and we're in the middle of it right now. Yeah?
I mean, I think it won't actually change the observational consequences of general relativity. It will change the way we think about it, and above all, it has the potential, I think, to change the way we think about the Big Bang and possibly black holes.
Exactly. Because if the divergence in the initial singularity is coming from this scale, which is gauge, then there's no reason to interpret that as a singularity.
Yeah.
Okay. And Tim is also going to be talking. Julian mentioned this in his talk. It's just a different version of it. Now, okay, I'm kind of out of time. I wanted to say something about, I think I said actually a lot of this. It's just that, look, people will say, yeah, but you're choosing a surface of simultaneity. That's against the spirit of general covariance. But, and this just goes back to what George was saying, no. Using gauge invariant equations of motion, diffeomorphism invariant equations of motion was to describe processes in a way that don't privilege any particular thing. But once you have real processes happening, they do give you privileged structures. Describe them using one representation of the degrees of freedom, and that's good enough. Okay. All right. Okay. Oh, this is just the summary, but I already said it. Okay, so yeah, I'm kind of out of time. I wanted to say that we've done a lot of work since 2010, and one of the things that it kind of goes along for the ride, and that's not completely true. There are some issues because when you have vacuum GR, the York slicing, under the way certain conditions are satisfied, that slicing will cover the whole space-time. Once you matter, that's not necessarily true anymore. It depends a little bit on the kind of matter that you introduce. So you can get situations where the shape dynamics solutions are different, globally different from the GR one. So locally they're the same as GR, but globally they give you different results. And we've been exploring. The first one that we looked at was, Enrique looked at, was Schwarzschild. Later, but this is a very idealized case. The shape interpretation is not so clear. Flavio, Tim, and graduate student named Napolitano. Okay, yeah. A lot of work on the twin shell, and if you read Flavio's book, you'll get a lot of the details on the twin shell. We did some stuff to connect things that people said ADS CFT. You might think, it's a theory of gravity with conformal symmetry. There must be links to insights about the Big Bang, and that's it. Yeah, I'm going to end there. Thanks.
Do any of the students plot? I'm going to be student before that.
I was just...
Thanks for a great talk, Sean. I have a really basic clarificatory question. It's really sort of low level. So when you talked about the symmetry trading in phase space, the reason that you couldn't do that in velocity phase space was because the Lagrangian has certain symmetries, but then there are certain symmetries that are variational symmetries that the rest of the that the Lagrangian that is to say that the Lagrangian doesn't have except when ds is equal to 0. And it seems like, at least on the Lagrangian side, that motivates a kind of different way of thinking about these two kinds of symmetry. And then when you put it into the interface space, you've got this one surface, you've got this other surface, and now you say you can flip them because the physics just lives.
Yeah.
Is there so what happens to the Lagrangian interpretation of those symmetries when you do the flip?
That's a really good question. So I actually don't know, but yeah, like I guess that's. But your point is good that just by looking at the Lagrangian symmetries, you can't tell what the observables are, and in general relativity, that's just true. And so when we say that the observables are scale invariant, people are always shocked. But you say, yeah, but there's a lot more symmetry than meets the eye, and it's not obvious by looking at the Lagrangian. Now, what is the Lagrangian formulation of symmetry trading? I tried to think about this carefully before the talk. I couldn't come up with anything. I think Tim has thought about this as well. None of us. It's a really good question. I don't think we know the answer. Maybe Stefan will talk about it in his talk. I don't know. Yeah.
So the floor's open for everyone. Please put your hand up. Okay, I'll see if I can remember that. James was first, though.
Yeah, apologies for have to this awkward question.
No, it's good.
But
I'm ready.
I mean, there's not a great history of people saying like everything in science comes down to this kind of observation. You know, why stop at kind of spatial, quasi-local comparisons of length? I mean, you know, I can just imagine someone saying, "Oh, everything in physics comes down to something in your consciousness or something," right? But that would be a really bad thing to kind of
reason anything about science on the basis of, right, yeah, of course in the end we know stuff through, thinking about it, but we don't want to make that pivotal to the epistemology of science. So I was just wondering, what you think about that, and then the maybe more substantive question is about scale invariance. Hasn't science taught us that there are lots of things that aren't scale invariant? So all kinds of phenomena in 3 dimensions where things don't scale up, because of the way the dimensions work. So things that are viable as structures at small scales aren't viable as structures at big scales. And then more particularly, I was just thinking of things like Planck's constant and the speed of light, telling us that there's some kind of fundamental quantities that are dimensional.
Okay, no, that's a great question, and I think that
the second one.
the second one I've already forgot about. No, but I think before I answer, I think I should say that probably you'll get a different answer from each of us. But I'll try to give my answer, which I hope is close to some people's answer. But we don't want to say that there aren't processes that you can model in a way that depends on the scale. But those would be processes where you're trying to describe a subsystem of the universe, and there are some external rods and clocks that are there, and they're part of the structure. So in that situation, it's totally justified to model that, to represent that using a scale, which is the thing that you just find is set by your external rods and clocks. So really, the epistemic argument only comes by thinking about the universe as a whole. So it should be relevant to something like cosmology. And the role of the Planck scale is really, really interesting because, when I wrote the dynamical similarities, the constant that comes out of the action. But that will change the path integral, right? And what quotienting by dynamical similarities means at the quantum level is something that I don't think anybody's thought about. We've thought about it a little bit. It's an open question. It's really, I think, an opportunity to make some interesting progress that people haven't done before.
I'm going to cut you off because you've got this question.
Okay, good. Yeah, good. I didn't want to answer your first question anyway.
So, what's the final aim of the shape dynamic? They try to show the local scale symmetry in whole physics, right? That's the aim of.
I think so. It would be. I think if you wanted to write down the most extreme goal, it would be something like when I said Barber's shape hypothesis, right? It would be, can we do it one damn shape after another, using the shape? And maybe they're not. Maybe I don't know. The fundamental theory will also obviously involve matter, so it will represent these shapes in some way. But the missing piece seems to be really kind of what Tim was talking about, modeling local measurements and not putting that in as prior, because my epistemic argument came from that. It came from, let's compare the rod to here. That's not something that you think about in GR, because in GR the Ricci scalar is an observable, right? Or at least the integral of it is a diffeomorphism invariant quantity. But that thing is not going to be something that you measure with these kinds of measurements that I was talking about.
Yeah, so can I come back to my question from the beginning and to get you to firmly commit on a yes or no on the question of whether shape dynamics does differ from GR on an observational level or not, because that may be slightly provocative. I mean, interpretations of physical models to some extent don't matter, right? What really matters is really only if models differ on observations, and interpretation is very nice to argue about, but it's not physics. So is there a physical difference between shape dynamics and GR?
I guess there's other people who want to answer first. I think at this point, the physical differences are subtle, but I do expect that quotienting by dynamical similarity will give real physical differences.
What's the experiment that I would have to do?
We don't know that yet. Or I don't know that yet.
I think there will be a difference in that the solutions that shape dynamics allows will be a set of measure zero of the solutions that general relativity allows, or a much smaller set, that it might be hugely more predictive than general. So a point I made yesterday in the discussion we had when we met up yesterday as a sort of a group meeting is that general relativity was based by Einstein on the assumption that in a sufficiently small space-time region, the laws of nature take exactly the same form. And then any cosmological solution is one in which the space-time satisfies that principle at every space point. Now, I think in shape dynamics, we're shifting from a formulation of the laws of nature as differential equations in infinitesimal regions to saying the law of specifying certain architectonic structure of the whole law of the universe. And that, I believe, is going to lead to a much, much smaller subset of solutions of general relativity. And in fact, this is coming out of the paper that I suppose Dave will be talking about with the so-called BKL conjecture in general relativity, for which there's increasing evidence, where you actually get a dense set of solutions of the BKL conjecture. You get a dense set of solutions of general relativity, but it's a dense set. So I guess that makes it a set of measure zero of the general relativistic solutions. So they have very characteristic properties.
Right. To rush a little bit. So you're saying that in all the experiments that we've done, which agree incredibly well, relativity, are all in this little subset. They're all in this little subset. Yeah.
So, but
if I can make
I think if we're on the right track, we will be able to make the best hope we have is to make a very precise statement about what the overwhelming majority of all initial data at the Big Bang will be like, which will then lead to very precise predictions about what should be observed on the sky. Maybe we will even be able to identify things which have been seen already, but nobody's realized they were significant.
A solution of general relativity that would be not part of this set and therefore forbidden by your
all the solutions of general relativity. Well, I think they will all be there. There's a question about black holes.
But you said that it's a set of measure zero.
No. Can I answer that, Julian? Do you mind if I? So all known solutions that we use for experimental predictions, like for black hole mergers or solar systems, all of those admit a CMC foliation. So there is discrepancy amongst us. What is the actual role of CMC foliations for shape dynamics that we can talk about? But if you wanted to go back and talk about that, all the solutions of GR, there, as Julian said, there are many more. There are many that don't admit the CMC foliation. It's just that the ones that we
Oh, close down there, look. Oh, okay. Yeah, go to the universe.
No.
Just go. Good example. I mean, I hesitate to say this because I know there's some disagreement about how we interpret it, but just if you look at the shape dynamics version of Schwarzschild, it's an Einstein-Rosen bridge. Now,
No, the question is that Schwarzschild, I don't know if the shape dynamic solution is that or not, but Schwarzschild, if you go all the way up to the singularity, that space-time does not admit a CMC foliation. What is the role for that for shape dynamics? I don't know. Maybe Tim wants to comment on that because he's thought a lot about it.
You're probably going to get into trouble with Kerr.
Yeah. Well, we've written papers about Kerr as well, but it's.
I'm sorry, you don't want to answer the question. Is there any other questions? I'm happy to let this discussion continue for a bit if there aren't.
I would just follow up on that a bit because I'm really a bit puzzled. In physics, of course, when you have a gauge symmetry, and that's part of what you discussed, you can look for gauge fixings. Mm-hmm. But these are typically not available for every solution, right? So this picture that you drew is very nice, but it's a bit of a cartoon because, of course, typically these gauge fixing conditions will not be good for all the orbits. Mm-hmm. And yeah, the CMC condition is one example here, I guess, which will not be available. So how are we supposed to think about this in terms of physics now? Are we supposed to say that the real space of solution is just the ones that admit CMC gauge?
I mean, it's the inversion of the principle. If this symmetry gradient principle would be the correct one, it would be the inversion. It would be, look, the actual solution space are these conformal systems, and you can gauge fix them by basically the GR, scalar Hamiltonian. And so those are the ones that admit to gauge fixing. It's a real inversion of it.
Well, from my perspective, I have a little wider perspective than what Sean was presenting, but from my perspective, tomorrow I will show some equations how to do that. Whenever you can decouple the evolution of the spatial conformal geometry from the local scale factor, that is a dynamical system that realizes the principles that Julian wants. Now, evolving in CMC gauge is one way of achieving that, but it's not the only way. There actually, you can split that into two problems. One is the initial value problem, and one is the evolution problem. The evolution problem you can satisfy in many. You don't have for the initial value problem. I don't know any better way of solving this problem than CMC gauge. But for the evolution, you can achieve the decoupling in many ways. And that is, so that is to answer directly what you were asking. And the other thing is, what would be a prediction? I mean, I wouldn't go as far as calling it a prediction, but the simplest cosmological model, the simplest class of cosmological models that you can build on shape space are Bianchi models. And if you look at them, then these models naturally develop something that is a cosmological constant, naturally have an evolution that looks like that has all the observational effects of a cosmological constant at late times, but at early times it deviates from a cosmological constant. So that is I wouldn't call it a prediction, but it's something that appears in the simplest models that you can come up with. So the simplest quantum cosmologies that you can build based on.
I'm going to give our speaker the last word. Do you have something you want to say in response as well? No. Okay, well, we've got half an hour coffee break, so let's thank you.